I'm going to talk about Bayesian semi-parametric models for binary data. It's a joint work with Carlinhos and Adriano Pope. The Bayesian framework is a set of Bernoulli-independent variables with probability of success, Pi. And the typical challenge is to model the probability of success, Pi, as a function of the covariable vector x and the parameter vector vector. The function f is a distribution function common in a scale location family of distributions. The inverse of f is the link function from generalized linear models. The usual strategy is choosing symmetric distributions around the zero. For example, the normal distribution results in the probability regression. The logistic distribution results in the logistic regression. Special attention is given for the logistic regression because of the interpretation of parameters. It's possible to talk about odds ratio from beta parameters. The odds ratio are central quantities in applied areas of research. But what about skewed probability curves? The real life is full of examples that the assumption of symmetric distributions is not adequate. If you want a right-skewed probability curve, the extreme value distribution for the maximum is an option. If you want a left-skewed probability curve, there is the extreme value for the minimum distribution. The literature has looking for solutions that avoid the assumption of a specific F distribution. For example, Prince, the well-known Landor-Das, and Stuckel in classical approach. The Bayesian parametric approach was begun with Albert and Chib in 1993. They considered each Bernoulli variable as a discretization of a double variable. And double is F distributed. Furthermore, F could be a scale mixture of G distributions with H distribution for the parameter of precision tau. Andrew and Mallows discussed scale normal mixtures, so they are our guide for scale mixtures. Albert and Chib, they consider the H distribution given by the gamma distribution. Then we have the t-student distribution with v degrees of freedom. If v is equal to 1, we have the Cauchy distribution. If v tends to infinite, we have the normal distribution. And they introduced the Kolmogorov-Smirnov distribution for the parameter of precision tau. So we have the logistic distribution. Chen et al. Presented a location mixture that results in asymmetric probability curves. But it's still necessary to specify the F distribution. The Bayesian non-parametric approach arises a solution to overcome the necessity in defining a specific F distribution. The foundations were present in Ferguson, 1973. The idea is, if F is not known, then it's a random quantity. Ferguson proposed the Dirichlet process as prior distribution for F. The Bayesian semi-parametric approach is similar to that introduced by Albert and Chib. Each Bernoulli variable is treated as a discretization of a double variable. The double variable is normal distributed with mean xi beta and precision tau I. Tau 1, tau L is a random sample from H. But the H distribution is random and beta distribution is random, is null. So we have two attribute prior distributions. For beta, we consider normal p-variate distribution. For H, we consider a Dirichlet process with baseline distribution H0 and dispersion parameter alpha. Our choice for H0 distribution depends on this F0 distribution. F0 is the prior expected F distribution, which is our interest. If H0 is gamma, then F0 is students. If H0 is homograph novel, then F0 is logistic distribution. The dispersion parameter of alpha could be fixed or random. If it's random, then we attribute a gamma distribution for alpha. The interpretation of alpha could be two interpretations. Alpha could be considered the degree of confidence we have about our base distribution H0, or alpha could be controls the number of clusters about the parameter of precision tau. Finally, you have the posterior distribution for double, H, and beta, which we can sample of the full conditional distributions of beta, H, and double. But the posterior distribution of H is not a simple Dirichlet process. It's a Dirichlet process mixture defined by Antoniak. It's not simple to generate a Dirichlet process mixture up to the algorithm developed by Escobar in 1994. He used the polyunic representation to integrate over the H distribution. It's a simple algorithm and efficient, but it's limited for conjugate cases. There are some solutions for non-conjugate cases, but it's for specific situations. An alternative algorithm is the blocked Gibbs sampler, presented by Sharma and James in 2001. They developed the algorithm based on the stick break representation. The idea is the truncation of the Dirichlet process. In order to apply this algorithm, it's necessary to rewrite the model with tau I is equal to ki. The z variables are the possible values of the precision tau. The k variables are classification variables, which associate each precision tau with a z variable. The q variables are the probabilities of the k variables. So we can sample from the H distribution, posterior distribution, through sampling the Z, K, Q, and alpha posterior full conditional distributions. We should look at with more details the Z posterior full distribution, full conditional distribution. Sample from Z is divided in two parts. The first part treats the Z variables that is not associated with any precision tau I. So we can sample the values from the baseline distribution H0. The second part treats the Z variables which are associated with some latent variable double. So it's necessary to calculate the posterior distribution between H0 and the normal distribution. And then we have two cases in this work. If you want F0 is T student distribution, H0 have to be the gamma distribution. Basu and his colleague use the polyunic Gibbs sampler for this case. It's okay. Because gamma distribution is conjugated with normal, so there is no problem. But if you want the logistic distribution in the Bayesian semi-parametric approach, it's interesting because we want to talk about alteration when we state prior distributions for beta parameters. Then H0 should be the homograph Smirnov distribution. It's necessary to insert a Metropolis Hasse step. It's easy when you use the block Gibbs sampler. Here it's only insert a rejection step. The Metropolis Hasse step was recovered from Chen and Deng, who developed the logistic regression in the Bayesian approach. We fitted these models to this data. It's a well-known data set. Bliss reported a study about adult fetal mortality. We consider three models: logistic Bayesian parametric, logistic semi-parametric, with fixed alpha and random alpha. We consider as convergence measures given by Brooks and Gelman. In this table, we have the MC conditionals. It's possible to see that the Bayesian semi-parametric models requires a greater computational effort, but we expect it. Because our models is more general. And then we have the estimates of the three models. The point estimates are very similar among the three models. The credibility intervals are larger from the Bayesian semi-parametric models because they consider they insert around the F distribution, which is natural. We consider as measure of quality of the model, to predict from the model, the sum of log of CPR. But here we can see that the Bayesian semi-parametric model, as well fixed alpha or random alpha, is really better than the Bayesian parametric model. And some concluding remarks. The Bayesian semi-parametric approach using the block Gibbs sampler is more general than the same approach with poly Gibbs sampler. We can consider Metropolis Hasse steps in a easy way. It's possible to elucidate prior distribution for regression parameters, talking about alteration, which is very interesting when we deal with applied insertions. The predicted intervals incorporates the inserted about the F distribution. That's all.